All right, demo E3. So this is one I gave as a mini exam in a previous semester with some small changes. So question one, we're starting off with two big flu networks. So these are communication and transportation devices, and we sort of need a network to sort of fly between these flu portals. And it also allows for sort of communication over distance. That's essentially what we're doing here. And we have two networks. And this is, we've talked a little bit about network effects. This is sort of historically why there's only been two networks, Fast Flu Inc. and SootNet. So we're given that both firms have a constant marginal cost of 40 galleons, and we're given the demand curve here. We're given the marginal revenue curve for Fast Flu and SootNet. So it turns out both of these two networks use a sophisticated ticketing system where they can charge a price for every trip, and then prices are also in galleons. And we're told here that the market is symmetric, so both of the two firms are facing a constant marginal cost curve that's identical, and the marginal revenue curves are symmetric. So all you have to do is swap the subscripts. Swap F for S, and you get the other one. Okay, so we're asked a few questions. The first question is to find the best response for the flu network. So this is a little bit of a misleading title here. We're asked to find the best response for Fast Flu. So we take the marginal cost curve and the marginal revenue curve, and we just set them equal to each other. So this is the solution to the firm's problem. And then we just use that relationship to then solve for what Fast Flu should do. So we have, the firm's problem for Fast Flu. So we're solving for the quantity that Fast Flu should produce if they knew what SootNet was doing. So this is our best response. We know no matter what SootNet is doing, we know what we should do. And then we do the same thing for, this title is a little misleading. The question is to do the same thing essentially for SootNet. So we solve for the best response for Fast Flu by setting these two equal to each other. So all we would do for SootNet is set marginal cost for SootNet equal to marginal revenue for SootNet. But because this game is symmetric, all we have to do is swap the subscripts for Fast Flu to get the best response for SootNet. So we just simply take this and then swap F for S and S for F because this game is symmetric. It's a really nice property. In the next demo, we'll talk about sort of a different setting where we don't have symmetric best responses. Okay, so for question 1C, we're asked to find the Nash equilibrium quantity and price. So all we have to do to find the Nash equilibrium quantity is play the best response against the best response. So what if both players are playing their best response to each other? This is a Nash equilibrium just like we've done in sort of a 2x2 context where we intersect the two best responses. What we're doing here is just intersecting the two best responses. So we take SootNet, and it actually doesn't matter which firm we start with. I'm starting with SootNet, so we take the best response for SootNet, and then plug in for QF what SootNet knows about the best response for Fast Flu. So we take Fast Flu's best response and plug it into SootNet's best response. So we have two equations, two unknowns, plugging one into the other allows us to solve for QS on its own. And when we plug this in and simplify, we get QS star, the equilibrium quantity for sootnet, to be 120. And then again, by symmetry, we don't have to do any additional work. We know both players are going to do exactly the same things because their marginal revenue and marginal cost curves are identical. The firm's problem is identical for both firms. So both are going to play exactly the same thing. And if you wanted to, you could go through and check the math, but it'll come out to be exactly the same. Okay, so we have the equilibrium quantity for both firms. We want the market quantity, so we just add them together. So Q star is just 240. We add 120 to 120, and that gives us 240. And then all we do is plug 240 into our demand curve. So we have this thing. So 400 minus 240 is just going to be 160. So we get our equilibrium price there. All right. And then the market profit, so the total profit for both firms in the market, is just going to be the price minus the marginal cost. And we can just do this in this way because both firms have the same marginal cost. We'll see an example where that isn't true in a different demo. And then we multiply it by the quantity in the market, which is 240. So we multiply 160 minus 40 times 240, which comes out to be 120 times 240, which gives us this number. All right. So that's question one. Question two, like with most sort of infrastructure projects, like utilities and like internet, for example, it's really costly to sort of have two networks operating at the same time in the same spaces. So it's sort of natural, right, for there to be one network that's formed through a merger. So part of this question is really asking what happens in the market after we allow this duopoly to merge. So we're forming a new Flu network, which is One Wizard International. The ministry made an argument here about the effect on competition, but One Wizard sort of lobbied the government to allow them to pass this merger. Okay, so again, we have a constant marginal cost at 40 galleons and a marginal revenue of this thing, which, if you'll notice, is the same as this marginal revenue curve, except we're setting this quantity, the quantity of the rival, equal to 0. There is no other rival. So this thing is 0, and the rest of it remains the same. So if you wanted to skip a step, you could look at this, the best response for one of the two firms and just set the rival's quantity equal to 0. And so that will be our hypothesis here, that quantity S, or quantity for one world, is equal to 180, where we set this thing equal to 0. And in fact, that's exactly how this goes. So we set the marginal cost for the firm equal to the marginal revenue, and then we just solve for Q. So Q star for one world, Q star O, is equal to 180. And when we compare this to the quantity in the market before the merger, which was 240, we can see that the quantity went down. Quantity went down after the merger. Okay, and then we're asked for post-merger price. So what price will one world charge after the merger, and how does it compare? Well, we just take 180 and plug it into the demand curve. One World is the only supplier of trips and communication in this market. They're a monopolist. So we just plug in their quantity, and that gives us 220. So comparing 220 to the original price of 160, prices have gone up after the merger. Okay, so we're seeing some of the effects of market power in this question. We have setting the quantity lower and setting the price higher, which intuitively should sort of give us some flashbacks to monopoly with deadweight loss. We've increased the size of the deadweight loss. All right, and then the last question here, we have profit after the merger. So profit is just price minus marginal cost in this case, which is the same as ATC when we have a constant marginal cost and no average total cost. Excuse me, no fixed costs. So we have 220 minus 40 times the quantity, which is 180. So we get 180 times 180. You plug that into a calculator and you get 32.4. Okay, and when we compare that to the profit before the merger, the profit from both firms, which was this thing, we can see profits have gone up. So profits have gone up, deadweight loss has gone up as well. Although here in this question we haven't explicitly asked for it. All right, so that's a complete answer. I think we'll leave it here.